Okay, this chapter, as you can see, the title deals with the concept of temperature. Okay, so here are the first four chapters. The first four chapters are the subject of thermodynamics. What does the word thermodynamics means to you guys? Does it say anything to you? Yep.
It's the flow of temperature change, basically.
It's the flow of heat.
Heat, sorry.
Thermo is heat, and dynamics is the subject of motion. Okay, and when does heat flow? Yep.
Change in energy.
Well, when will heat flow between two objects?
The temperatures are different.
When the temperatures are different. Okay, so the temperature will decide which way the heat will flow. Okay, and heat always flows from a higher temperature to a lower temperature. Okay. These four chapters will become an entire course in your junior or senior level. Okay, so so you're getting an introduction to that subject. Okay. Now, all laws of physics apply to systems, various systems, and thermodynamics. The laws of thermodynamics apply to systems with a large number of particles. So if you have 10 particles in a system, you don't use the laws of thermodynamics. Okay? You have to have the system has to contain a large number of particles. What do I mean by large number of particles? 10? No, I already said that. 100? 200?
Is it an infinite amount?
No. Anything like Avogadro's number of particles. What is Avogadro's number? I'm sorry?
6.023.
10 to the 24. So, okay, so you're talking about billions and trillions of particles. Okay? So you got to have Avogadro's number of particles, and then you start using laws of thermodynamics. All right. Can you think of an example of a thermodynamic system? I'm sorry?
An engine.
An engine. The gas in this room, this table is a thermodynamic system. You are a thermodynamic system. Okay? Any large particle system. Okay. All right, so now that we know what these things apply to, okay, so thermodynamics is a branch of natural science concerned with heat and its relation to energy and work. Okay. So this subject arose from the fact that so we started when we invented the steam engine and all that. Well, how does a steam engine work? You burn coal, you boil water, and you get the steam to do work. Okay. And then you started asking the question, what is the maximum amount of work you can get done? Okay. When you go shopping and stuff like that, what do you want to do? You want to get the best bang for your buck, right? Okay. So you generate heat, and what do you want to do? You want to get the most amount of work you can get. Okay. So and a lot of our systems are set up that way. So for instance, let's say this object is at a height. What does it have? It has potential energy. How much potential energy does it have? mgh. How much of this energy can be converted to work? 100% of it can be converted to work. Okay? So if you had 1,000 joules of potential energy, you could make this drop, and using a pulley system, you can make another object go up. So you can convert 100% of that to work. Okay? Now, so if I gave you 1,000 joules of potential energy, you can convert it into 1,000 joules of work. That's assuming you had a frictionless system and all that. I give you 1,000 joules of heat. Okay, so for instance, you burn gasoline in your car, okay, and let's say you generated 1,000 joules of heat. How much of that can you convert to the motion of the car? 200 joules. Your car is 20% efficient. Every time you put $5 of gasoline, in the car, you're getting $1 of motion. What happened to the other $4? It remains as heat. It went out of your tailpipe. Okay? So thermodynamics arose from that kind of stuff. You know, you are producing heat by burning stuff, and our systems are set up that way, and then you're trying to convert some of that heat to work. Okay? All right, so it's an important subject. A lot of our electricity is produced that way. What do? We burn coal, produce steam. The steam turns a generator to produce electricity. Okay? All right. Now, the laws of thermodynamics can be applied to a wide variety of topics in science and engineering, and it turns out. So anytime there's a lot of particles involved or a lot of interactions involved, it turns out that you can use the laws of thermodynamics, okay? Results of thermodynamics are essential for chemistry, chemical engineering, aerospace engineering, mechanical engineering, cell biology, look at this. And even in economics, we've found that, you know, so for instance, you can apply in the stock market trading. There's a lot of interaction and all that, I guess, and you can apply that. Okay. So what is can you give me an example of a thermodynamic system? Again? Yep. Yeah, your refrigerator, you're a thermodynamic system. The gas in this room is a thermodynamic system. Okay? How many particles are there in this system? How many gas particles are there in this room?
10 to the 24 plus.
Yeah, so 1 mole is Avogadro's number, 10 to the 24. There's about 10,000 moles in here. Okay, so there's about 10 to the 28 air molecules in there, mostly, N2 and O2. This many particles in the air in this room. And I want you to, and so let's say we want to describe this system. Okay? We want to characterize this system. What will I give you when I want to describe this system? Yeah?
Maybe volume,
It's volume,
heat capacity.
it's temperature, it's pressure. I'll give you 5 quantities to describe this. There's 10 to the 28 particles. So that's amazing. So these are systems in equilibrium, okay? And you'll describe the system by a few parameters, okay? So, and these are, and of course, this is when it's in equilibrium. Let's say if the temperature was different at different points, then you would have to have the temperature as a function of position, and that's giving a lot more numbers. But still, nowhere near this guy, okay? So we'll study thermodynamic systems mostly in equilibrium, and you will be characterizing the systems with very few numbers, okay? So these are the 4 laws of thermodynamics. The 0th law says, so there's one chapter dedicated to this law, there's another chapter dedicated to this law, okay? And so on. The 0th law says when objects are in thermal equilibrium with each other. What does that mean? Thermal equilibrium. Okay. I'm sorry? Yeah, so they are in thermal equilibrium when they're at the same temperature. But thermal equilibrium means 2 objects are not exchanging net heat energy. So this guy is in thermal equilibrium with the table. So are they exchanging any heat at all?
No.
They are exchanging heat, but there's no net heat. This guy is giving, whatever this guy gives, that's how much he's getting back. Okay, there's no net heat. Now, this is not thermal isolation, they're still exchanging heat. But if you were isolated and you're not exchanging any heat, then you're thermally isolated. Thermal equilibrium doesn't mean, okay, you are able to exchange heat. For instance, if you are in thermal contact, okay, when you're in thermal contact, you can exchange heat. Okay? Okay, so when you're in thermal equilibrium, you are at the same temperature and you're not exchanging any net heat. Okay. So the first law of thermodynamics, there's something called internal energy, and that is heat. Okay, we'll come to that in a second. And how it's related to energy transfer and work done. Okay, simplistically, you can think of this as just a conservation of energy principle. Okay, so the first law of thermodynamics is just a conservation of energy principle with heat taken into account. The second law of thermodynamics, you've heard of quantities called entropy and stuff like that. Okay? Okay, let me go back to, I'm just giving you an overview here. Okay. How much of this potential energy can you convert to work?
100%.
100%. How much of heat can you convert to work?
20%.
So in that system, in your thermodynamic system, your car, you can convert 20%. There are coal power plants where 40% of the heat can be converted to. Okay, so it depends on the temperature difference you're operating on. Entropy sort of tells you how much of the heat you cannot convert to work. Okay, so that's what the second law of thermodynamics is related to. Okay, and third law of thermodynamics is related to something called absolute zero, and we'll come to that in a second. Okay, so anyway, we'll talk about these over the next 4 chapters. Okay. So what does temperature measure? It tells you how hot an object is. Okay. So let me show you a little app. Does this record when I show them? Mhm. Right, so I've taken a gas here. It's at 300 degree Kelvin, and the pressure is 30 atmospheres. Okay. So the temperature is 300 degree Kelvin, the temperature of this gas, and that tells you how hot that gas. You will learn over the next couple of chapters, this measures the average kinetic energy per particle. Okay, so when you say how hot an object is, the temperature is telling you that property. It's telling you average kinetic energy per particle. Okay, so if I speed up all the particles, then the average kinetic energy is increased, and so the temperature will increase. Okay, and so you can watch this. So I'm going to heat this gas. See, the particles are speeding up, and watch the temperature. See, the temperature rose to the. Okay. So temperature, which tells you how hot an object is, like I said, you learn that it measures the average kinetic energy per particle. Yeah. What's the temperature of this guy?
524.
Huh?
Wait, what did you point to?
The temperature of this table.
Room temp.
Room temperature, which is about 22 degrees Celsius, which is the temperature of the air in this room. That's the temperature of this guy. So I just told you temperature is a measure of the average kinetic energy. Well, you can understand this guy, the gas molecules going around. What does the temperature here mean? Okay, so here's a model of a solid. Here's a model of a solid, okay? So in a solid, the atoms are fixed and there's intermolecular forces modeled by these springs. And are these atoms still? No, they're vibrating about their position. And so their average kinetic energy is exactly same as the kinetic energy of these air molecules. Okay? The temperature of the wall is the same as the temperature of this table. Okay. So even in those solids, those molecules are vibrating about their average position, okay, about their equilibrium position. Okay. So all inanimate objects in this room are at the same temperature. And the average kinetic energy per the particle is the same. Okay? So that's what temperature measures. All right. So okay, so how hot an object is, it's a measure of the average internal random kinetic energy per particle of the system. Okay. You will elaborate on that, and we'll add to that later in the chapter. Okay, so when the universe first began, 13.8 billion years ago, the temperature was about 10 to the power of 39 Kelvin. Okay. Today, the background temperature, you are bathed in radiation. The whole universe is bathed in radiation, which is the cosmic microwave background radiation, and that's at 2.72 degree Kelvin, and we'll come to that in a little bit. Okay, thermal contact, as the name suggests, thermal contact means you're in thermal contact with an object if you can exchange thermal energy with that object. Okay? What are you in thermal contact with?
Stable.
This table. You're in thermal contact with everything in this room. How are you in thermal contact with the wall?
The air.
Hmm?
The air.
Yeah, they're air, but mostly through electromagnetic radiation. Okay. All right, so we are in thermal contact with every object in this room. Okay. Now, the strength of the thermal contact can vary. So right now, this guy is in thermal contact with the table. That contact is strong. Now the thermal contact got weaker. Okay. So we're not. All right. So energy can be exchanged one of three ways: via conduction, convection, or radiation. So our friend just said that we are in thermal contact with the wall through air. That's convective heating. Okay, so what's going on is I am warmer than the table. So I warm the air around me. When you warm the air, it gets lighter than the surrounding cold air. It'll rise up and then go hit the wall and transfer some of the heat. Okay, so that's all right. Thermal equilibrium. Two objects are in thermal equilibrium if they don't exchange net heat. They are exchanging heat, okay, so they have to be in thermal contact. They're in thermal contact. So if they don't exchange net heat, then they're in thermal equilibrium. And that happens when they are at the same temperature. So two objects are in thermal equilibrium if they do not exchange net heat. Two bodies in thermal equilibrium have the same temperature. The zeroth law of thermodynamics just says if A is in thermal equilibrium with B and B is in thermal equilibrium with C, then A will be in thermal equilibrium with C. Okay? If A is in equilibrium with B and B is in equilibrium with C, then A and C will be in equilibrium with each other. Okay? That's all. All right. Touch that table. Touch your computer. No. Which one is colder? Which one is hotter?
Computer's much colder.
Okay. Everybody agree? They're exactly the same temperature. That guy is not a good thermometer. what's going on? So we've established one thing, he's not a good thermometer. What we are sensitive to is, see, we have a finite source of energy. Okay? What we are worried about is losing or gaining energy too fast. So we are more attuned to loss of heat or gain of heat. That computer conducted heat away from faster from his body than the table did. So it felt colder, okay? And so you don't want to hold on to something cold very long, you lose too much heat. Okay? So humans are, to a large degree, sensitive to energy fluxes rather than temperatures. Okay? So we are not good thermometers, but we can sense heat gain or loss, fast rates of heat gain or loss pretty well. You touch a hot plate, you remove your hand fast. Why? Because you're getting heat coming in fast. When you just touch it, enough heat has not come into your body to burn you. But you react fast because you know that at that rate of flux, you'll burn soon. Okay? So anyway, so here's another example. You can verify yourself on a cold, dark morning in the outhouse on a mountain cabin equipped with a wooden and a metal toilet seat. Both seats are at the same temperature, but your backside will, which is not a good thermometer, is very effective in telling you which is which. All right, so temperature tells you how hot an object is, okay? And we all want to measure the temperature of objects and stuff like that. In science, we want to make measurements. So there are various scales, and these are the three common scales we use to measure temperature: Celsius, Fahrenheit, and Kelvin scale. Okay, so here's how you define a scale. Okay. It turns out that in physics, phenomena happen at the same temperature. So for instance, at one atmospheric pressure, ice will melt at the same temperature. Today, tomorrow, 10 years from now, in this galaxy, in the neighboring galaxy, at one atmospheric pressure, ice will melt at the same temperature. How do we know? Every time it melts, you put your finger, it feels the same. Water will boil at the same temperature at one atmosphere. If the pressure is different, so if the pressure is lower, then water boils at a lower temperature. So for instance, at high altitudes, if you're climbing Mount Everest, for instance, and you boil water, at lower pressure, it boils at lower temperature. But at one atmosphere, it boils at the same temperature. Okay, so here's how you make a temperature scale. You call the melting point of ice something, and the boiling point of water something else. Since this is hotter, you give it a bigger number. And since this is colder, you give it a smaller number. What number do you want to give? Anything you want. Okay? So on the Celsius scale, this is called 0 degrees Celsius. This is called 100 degrees Celsius. You want to make a finer temperature scale. Then you call this a 0 degrees Celsius, and you call this 1,000 degree, whatever. That became a scale that is 10 times finer. Okay? So how many temperature scales can you make? Infinite, as many as you want. Okay? So you see the Fahrenheit scale is finer than the Celsius scale. See, 32 degrees Fahrenheit and 200, that's 180 degrees. Okay? This is twice as fine as the Celsius scale. Okay? Here's a Kelvin scale. This is called 273 degree Kelvin and 373 degree Kelvin. You see, this is 100 degrees in between these 2 points and 100 degrees here. So it looks like this is a redundant scale. So why do we have those? Mhm.
Kelvin scale starts closer to absolute zero, or it starts at absolute zero, so it's more applicable. It's easier to use with like really cold things in the universe, I think.
All right, so here we go. All right, so here's gas particles. Yeah. I'm going to cool it. What's happening to the gas particles?
Just went down.
Hmm. What's the best I can do?
No movement.
Hmm?
No movement.
Stop them all. That happens at minus 273 degrees Celsius. That's a very odd number, so you just call it 0 degree Kelvin, that's all. All right. So that's how it was discovered. Okay. So actually the way we discovered it was, you see, all right, so this is 300 degree Kelvin, okay? Now what I'll do is, in this container, I took this amount of gas. In another container, I'll take more gas. The pressure is higher. The temperature is the same, okay? In another container, I'll take more gas, and the pressure is higher. So this is the experiment we did. So in 3 containers, we took gas at 100 degree Kelvin, 100 degrees Celsius, and started cooling them. The molecules got slower, and all the molecules came to rest at the same temperature, minus 273 degrees Celsius. Okay? And telling your little brother that minus 273 degrees Celsius is the lowest temperature, you'll never convince him. He'll always ask why, so you just call it 0 degree Kelvin. Okay. So that's how absolute zero was discovered. Okay. So to make a temperature scale, you need two physical phenomena that are repeatable, okay, and happen, and you call those two temperatures. So now this is dealing with water. You got to have pure water and all that kind of stuff. So here's two phenomena that are absolutely unambiguous. Absolute zero, everybody understands. Okay? You can never get to absolute zero, but that's one point that we choose. And the other point that is chosen for precise scientific measurements is the triple point of water. Okay? And let's see what the triple point of water means. The triple point of water happens at 0.01 degrees Celsius, okay, at that temperature. So there's the absolute zero. All right, so we want to understand this phase diagram. Okay, so every substance has phase diagram. Well, these phase diagrams are important, and we have phase diagrams for many substances. Okay, so what this is for water. Let me start off by saying that this is a funny scale. See, it's not a linear scale. It's not a log scale. But it's used to illustrate certain points. And the two parameters are pressure and temperature. You can use other parameters, okay? And you see phase diagrams with other parameters. Okay. What this tells you is, if for the substance H2O, this is the pressure and that's the temperature, it will be in the liquid state. Okay. So for these parameters, for these values, it'll tell you what state it will be in. Okay, so at this pressure and this temperature, you can't have solid water. You can't have gaseous water. It will be in water. It'll be in liquid state. If you're at any of these pressures and temperature, then water, the liquid and vapor can coexist. At these temperatures and pressures, solid and liquid can coexist. Okay? At these temperatures and pressures, solid and vapor can coexist. Okay? So for instance, and this pressure is the vapor pressure of water, is the vapor pressure. So if the vapor pressure, if the air is very dry, and I don't know, I've not lived in a cold region, but ice can sublimate directly, okay? And so when ice on the ground suddenly evaporates, it's sublimating directly, okay? See, at this pressure and temperature, see, all three phases can coexist, and that's the triple point of water. Okay. So here is a triple point. So, and so to have all three phases coexisting, you have to be at precisely this pressure, 0.006 atmosphere, and this temperature. Okay. So we use that to define that temperature. And you see, if you add heat, you can convert all of that to water vapor or to liquid, or if you remove heat, you can freeze all of that to ice. So the three phases of water can coexist at 273.16 Kelvin and 0.06 atmospheres. At this point, it's possible to change all of the substance to any phase by making infinitesimal changes. Okay. So, again, why are we talking about this? To make any temperature scales, you need two phenomena, okay? And so, for precise definition of temperatures, the 2 points that are used are absolute zero and the triple point of water. But for everyday things, these scales are good enough. These are, for stuff that we measure in our life, these are the three scales that are used, okay? So, and these two formulas tell you how to convert a temperature from Celsius scale to Fahrenheit scale. And this tells you how to convert from Celsius to Kelvin scale. Okay. So 27 degrees Celsius, 27 plus that is 300 degree Kelvin. The temperature in this room is 22 degrees Celsius. So it's 295 Kelvin. Okay. Now, Celsius to Fahrenheit, here's the easy conversion. See, this is approximately 2. So if you want to convert 20 degrees Celsius to Fahrenheit, 20 times 2 is 40, 40 plus 30 is 70 degrees Fahrenheit. So 20 degrees Celsius is about 70 degrees Fahrenheit. Okay. So here are some temperatures. Okay. Inside the sun, in the center of the sun, at the center of the sun, the temperature is 15.6 million degree Kelvin. Okay. At the center of a hydrogen bomb exploding, the temperature is 100 million degree Kelvin. So how did they get the temperature of that and that? Well, that's a longer story, but how did they get the temperature of that? All right, so now let's understand that. Okay. Okay, all objects emit electromagnetic radiation. You are emitting electromagnetic radiation. This table is, the wall is, and so on. Okay, and so if you're a black body, this is a black body spectrum. Black body, for our purposes, you heat any solid or liquid, it'll emit a spectrum like this. What this tells you is this is the intensity of light and as a function of wavelength. At this wavelength, this object that is at 5,800 degree Kelvin, which is the surface temperature of the sun, at this wavelength, it's emitting that intensity. At this wavelength, it's emitting that intensity. At this wavelength, it's emitting that intensity. Okay, so this is what the sun emits at this temperature. But if I heat this table to that temperature, it'll emit exactly this thing. Okay, this will be the spectrum. Let me change the temperature and tell me what happens to the curve. The curve changed. The curve is unique for every temperature. Okay? So if you want to measure the temperature of any objects that you don't want to touch with your finger, all you have to do is measure the intensity of different wavelengths coming from that source. And that's how we know the temperature of the atmosphere of some planet. You want to measure the temperature of the explosion, the hydrogen bomb explosion. You're measuring the intensity of radiation of various wavelengths coming. That's how those thermometers, no-touch thermometers work. Okay. So that's how you can get the temperature of a furnace. You're measuring intensities of various wavelengths of light coming. Okay. Okay, so here are some of the temperatures we measured. Look at that. So I'm just going to point out a couple of things. The center of the sun is 15 million degree Kelvin. This is relativistic heavy ion collisions. So this is about 10 to the 6 Kelvin. This is 10 to the 12 Kelvin. 1,000,000 times hotter than the center of the sun. So in large colliders, we collide heavy ions, and in the collision, the temperature can get that high. The coldest temperature we've gone to is about 10 to the minus 10 Kelvin. Again, so very close to absolute zero. But we can not get to absolute zero. Okay? Okay, we can take a 5-minute break.